So, let me erase this. All right. Circle.
I think you're in the way. Okay. You're good.
Let's assume that that's a good circle. That it's a perfect circle. This is the x direction. This is the y direction. This point is 1. Actually, negative 1. This point is 1. This point's negative 1. And this point's 1. So if we look at our Cartesian coordinate system, x comma y, to define 2 points in space, or a point in space, right?
Shouldn't those be parentheses, not brackets?
Depends on, doesn't matter. So this is at 0 comma 1, if you want to do it this way. This is at 0 comma negative 1. This is at 1 comma 0, right? And this is at negative 1 comma 0, right?
Uh-huh.
Now, this is a unit circle, so that means that no matter where I go, yeah, somebody's gotten goop on my whiteboard. I'm trying to ruin it. It means no matter where you go, if I go here, what's this distance? R.
1.
1. This distance is 1.
So before you draw the line and put the gap there, this is 1.
Correct.
So then that makes it less.
Right. This is 1. Is the unit, is the distance. R is the radius of this circle.
Mm-hmm.
D would be 2R, right? That's
Diameter.
the whole diameter. Now, when this connects over here, we see if I make this a right angle, so I'm going to create a right angle by drawing a line from here down to the x-axis. I can also create one the same way over here, right?
And then that's special right triangles in a square.
This is any number of special triangles, yes, but right now I'm not worried about that.
I was just saying,
So,
asking.
now, this distance here I'll call OPP. No, I'll call it ADJ
Adjacent.
for the adjacent side.
And then this one's
This I'll
opposite.
call OPP for the opposite side.
Ow.
This distance of this length of the adjacent side, the term is the projection of the radius onto the x-axis. The reason it's called the projection is, think about it, well, this is an example, this is the actual reason. Think if this was a light bulb up here. Shining down on this. If this was a light bulb shining down.
Light bulbs don't shine like that. You have to draw it upside down.
Yeah, I know. But it would make a shadow, right? It would project a shadow onto this line. This is actually how Pythagoras and people a gajillion years ago figured out what the diameter of the Earth was. Drive a tall pole into the ground, and when the sun's at a certain angle, sun's over here,
It makes a line.
it makes a shadow. You know this is a right angle. If you do this at a couple of different positions, you can triangulate where the sun is in relation to both. And if you know that it's on a circle, you can figure that arc length, you can figure the distance around the Earth. Christopher Columbus did not figure out that the Earth was round. Everybody already knew it.
I know that.
When I was a kid, they taught that he discovered the Earth was round.
Yeah, they taught that they thought the world was flat.
Well,
and then,
people do, and people still do.
No, but they taught that they thought the world was flat, and they went off and sailed it. Like, if you thought the world was flat, why would you sail if you thought you were going to sail off the edge?
He was proving that it wasn't flat.
But what if he was wrong and he sailed off the edge? Like,
He was looking for a shorter trade route to India.
yeah, but he didn't go to India.
Everybody in the world who knew that the world was round knew that going over the sea towards the soon-to-be-discovered Americas was a longer way to get
But
to
I thought
India.
Leif Erikson discovered them. Like North
Well,
America.
I'm talking Spaniards and whatever, right?
Oh,
Europeans.
like colonized, discovered.
Right.
Okay.
Those guys knew it was actually quicker to go to, the smart guys actually knew it was quicker to go over land to India than it was to go around over water. Because they did the math and said, you gotta go way around. Anyway, so
I didn't even make it to India.
now if we imagine, well, let's not go there yet. So trigonometry is all based on this circle, these relationships here. So the sine of an angle, let's see if I can draw a theta in here. Theta, the sine of the angle theta is equal to the adjacent.
No.
Did I have it wrong?
Opposite.
Yeah, you're right. Opposite
Over hypotenuse.
over hypotenuse. So it's the opposite side. And what that is this length here, this angle in degrees or radians. You got to make sure your calculator's
It's
set right.
degrees.
A radian and a degree are just different measures of the same thing. It's like yards and meters.
I know, but
It doesn't matter as long as
Huh.
you keep it in the right form.
neat.
A degree and a radian is sort of similar to feet and meters.
I
Just
have a question.
different unit of measure. What?
When you're doing sine and cosine, you do like the opposite. So this is the angle you're doing, and it's the opposite of this angle. So if you were doing this angle, would it be this is the opposite and this is the adjacent?
You wouldn't do this angle, you'd do this angle.
No, but no. Okay, let me see the marker. If you have a triangle and right triangle, normally it's like this angle, so this is the opposite and this is the adjacent.
Mm-hmm.
But if you were doing this angle, wouldn't this is the opposite
Yes.
and this is the adjacent?
Yes,
Okay, so it's
Absolutely.
opposite the angle, not the hypotenuse.
correct. It's opposite the angle and adjacent to the angle, which means that it's one of the legs of the angle.
Okay.
So if I want to find out how many degrees this angle is, or radians, depending, then I can take the opposite and divide it by the hypotenuse and get the actual angle. Or I actually get the sine of it and then I take the... So
Yeah, I got it.
conversely, if I know what the angle is, in this case the hypotenuse is what?
1.
So if I do some simple algebra, if I multiply both sides times 1 sine theta is equal to the opposite side. The opposite side is the sine theta. So this distance here is sine theta. Now I just found one of my coordinates in space for this, right? So that tells me that's sine theta.
I'm gonna write this down.
And I wrote a phi instead of a theta, but you can't tell. So. Actually, that was y. So it's...
I'm still writing alpha because we started with alpha and that's what I have.
Okay. So we know that opposite is this distance. So my coordinates of this spot on the circle here, sine theta. And now I can do a maneuver here.
This point.
Yep. So if I want to find this position in space, how do I do it using what I have known written right here on the board right now? If I want to find the distance along the x-axis. And I'll give you a hint. This is a right angle because it's the intersection of two coordinate axes.
That makes all of them right angles.
It does. So what is the angle, I'll call this one beta, since you have alpha written down somewhere else. So if this is theta and this is beta, what's the relationship between theta and beta?
They're the same.
No.
No.
I don't know what theta is.
Okay.
I know
Ouch.
that this is a right angle, so I know that 90 is equal to beta
Plus
plus
theta.
theta. And if I already know theta, then that means theta is equal, I want to find beta. That means, yeah, 90 minus theta is equal to beta, right?
Yes.
Move. Oh, yeah, 90 minus theta is equal to beta. So that means then that if I want to know this distance here, now I know this angle and I know this. And this is the adjacent side now, right? Exactly what you were saying earlier for this angle, for this rectangle.
Because it's next to it.
Right. And so this is opposite. So I know that the sine of beta is equal to the opposite over the hypotenuse. The hypotenuse is 1 again, right? And so that tells me, which is also, just to throw it in here, the x distance. And this is the y distance over here. So when I do my math, I know now,
Where'd you put x?
right here,
No, what's x on there?
x is this distance.
Okay,
From here
well,
to
you
here.
didn't mark it. So.
Oh, I got too much stuff on here. So that tells me that x is equal to the sine of 90 minus theta. Right? Because it's this opposite side over here.
Oh, okay.
Right?
Um,
Because I'm not putting the opposite in there. I don't want to confuse things because now we're going to go back to a fundamental relationship. Because this y, or I'm sorry, this x direction, if I would want to find out what this distance of the adjacent is, x is equal to the cosine of theta, which is equal to the adjacent over the hypotenuse, right?
mm-hmm.
Which means that sine of 90 degrees minus theta is the same as cosine of theta. Okay, fine, alpha.
Oh, I already
Quit
have
stomping.
alpha.
I wasn't stomping.
Yes, you were. Now stop. All right. So, now,
I'm gonna have to get a new paper.
and then the tangent, of course, is equal to,
Opposite over adjacent.
it's the sine divided by the cosine, which is equal to the opposite over the adjacent, if you do the math, right?
Uh-huh.
Simple algebra. All right, now, let's imagine, so this is the cosine of theta, and, or it's the sine of 90 minus theta, right? What?
You did an eyebrow wiggle.
I shrugged my eyebrows at you. Now, this is what's, so this is the Cartesian coordinates.
What's that named after?
A guy named Cartesian, Cartesius, I think. He's the one who came up with The XY coordinate system is called Cartesian coordinates. Another way to describe this is called angle distance formula. So theta comma 1. I know that theta is some degrees angles, and I know that the distance out of the radius is 1. So this is the angle, and this is the radius, or the distance. So the only thing that changes if this is bigger, if this is a unit, so now,
Go to the rolling thing.
well, no, let's not do the rolling thing. Let's do a sine. Go back to the sine. That is the opposite over the hypotenuse, right? Sine of theta is equal to the opposite over hypotenuse, which is r in a more general term. So if I want to know the distance of the opposite side, it's r sine theta is equal to the opposite. Or r cosine theta is equal to the adjacent. So it doesn't matter what length this is, you already know it. You can actually go back to 1, right? You can actually just do the cosine of theta, and that'll give you the adjacent, and then you can just multiply it by r, and that tells you the actual length of the ladder that fell on the side of the house or whatever.
How do you just have a house ladder?
Huh?
I know what you're like trying to say, but how does a ladder fall like that?
Because idiots use ladders.
But it wouldn't
Me
fall
too.
that way. It'd fall
fall.
back.
No, it depends. You push it up to the point where it falls against the house so that you can climb up the side of the house. Or you line it up sideways and then you let it fall into the side of the house. I mean, it's a controlled fall. But... Okay. So now, let's imagine that this is a wheel. Let's take all this stuff out of it.
I'm going on the next page. I don't have room for this.
Yes.
Hi.
What's up? Don't lean on the vacuum, you will break it. So let's imagine,
Oh, the axes.
I did,
Well, I know. I'm asking. Do you want me to?
oh, I don't care. Imagine now that this wheel rolls this way.
I have to draw the wheel first.
When you're here, I want to make a new axis that parallels this one. Now these are, but we're doing it in two different spaces, two different units. This is degrees, 0 degrees, 1 degree, 2 degree, 90 degrees, 180 degrees. This is too much, too far apart.
Daddy. Daddy,
What?
can I put in the computer?
I guess so.
You just draw the squiggly line.
That's a dot, 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 dot.
But can't you draw the squiggly? Like if you have
No.
an axis, don't you? Isn't that like a break in it?
I'm not using it as a break. I'm just saying, and so on. 1, 2, 3.
Okay. So like 1 through 90 is in between here.
Yeah, and then 91 through 180, so forth.
Okay.
So if I start this off, and I use this is, so this axis now is theta,
Stop.
or in your notation, alpha. And this axis
Stop my area.
is sine theta.
Actually, yeah,
Still sore from your mom smacking you?
No.
You're like,
No, I gotta. My cheekbone hurts.
that's why I asked.
No, I smashed my face on her desk. I went to go like this to lay down my arm. I missed my arm.
Okay. So if this is sine of theta, and this is degrees of theta, what's the maximum and minimum this can ever be?
Well, wouldn't the maximum be 360?
No,
Or
no, sine theta.
oh,
This is the maximum and minimum of sine theta. What are they? Remember our unit circle.
oh, in this circle, 1,
So the maximum is 1, and what's the minimum?
-1.
-1. You will never go outside the bounds of this if it's the unit
Why
circle.
is it a dash there?
Oh, I'm sorry, that's because this other
That's
dash.
confusing.
Yeah, it is. So it's -1 and 1. So now, let's imagine I roll this down the road. So, like I said, so now we go over here somewhere, and this angle is now this, right?
This is ridiculous. I'm just gonna like redraw all this, that different angle thingy. My circle's ugly.
Adam. It's from Kayla. What is it? It says, I'm your Sarah had the same one as me.
So I will give you in full disclosure, I might be rolling the axis backwards here, but
Your sibling, the best number.
because we usually draw them going positive first. So that means I've got a little bit of stuff mixed up here. I'm going the wrong direction. Actually, no, it makes sense. I should roll it the other way. Let me roll it
Oh
the
my
other
gosh, are you kidding?
All I'm doing is changing the directions of arrows, and now it's...
But I just drew that line. I'm
That's
writing
all.
in pen. Are you kidding me?
It'll change the sign of everything. Yeah, whatever. I realized I made a mistake, and I'm trying to correct it so it doesn't confuse you later.
Okay, let's just pretend this line doesn't exist.
And just scribble out the other one. You already scribbled it out?
That's,
All right.
that's what I'm saying, pretending doesn't exist.
So we're going to say that it's actually rolling this way as it goes. What happens when we know that this is a 90-degree relation? So as my radius comes up, starts spinning this way, anti-clockwise. When it gets
Counterclockwise?
counterclockwise, anti-clockwise, you'll hear it called different things in different parts of the world. Don't yell at it. Don't laugh about it. That's how people... Anti means against.
I know
Counter
what
means
anti
against.
means.
Here in America, we usually say counterclockwise. In England and all the old territories, they usually say anti-clockwise. Because a counter is also one of those things. So, if I'm at 90 degrees, what is the value of sine theta?
I got 2 things from Dakota.
Sine theta is the distance in y, right?
He is in my class.
Do I have them backwards? I might have them backwards. Anyway. So, okay, if I've come all the way over to here, what's my value for the sine? Opposite over adjacent. What's the opposite? Well, let's start here. Let's start at 0. What's the value in the y direction if I'm here? What's sine of theta?
0.
Now if I come over to here, what's the value in the y direction?
1.
Sine of 90 degrees is 1. Sine of 180 degrees is y direction,
0.
0. Sine of 270 degrees is
-1.
-1. Sine of 360 degrees is the same as the sine of 0.
0.
0.
So it makes a wave.
Ah. Gadzooks.
It goes on that one.
Yeah.
You missed it!
God, I'm
Oh
bad
my
at this
gosh!
There we go. I'm bad at this today.
That was funny.
This is a wave.
Let me draw it. I want to draw it.
And the cosine does this. Because remember, a cosine is what? Theta minus 90? Right? 90 minus theta.
Yes.
So if theta is equal to 90, what's the cosine then? It's a nice curve. It's
Look,
not
I drew mine right.
Yeah, but it looks like a sawtooth.
Yeah, but at least I didn't have to erase it 5 times.
Okay, but now let's talk about a cosine. A cosine's the same as a 90 minus theta of a sine of 90 minus theta. So if I'm at 0, 90 minus 0 is what?
0. 90! Oh my gosh!
So a cosine starts here and does this.
Sawtooth.
Trying to get it right here. Comes here to there to there to there.
It looks wider.
This is 90
Gotta try
degrees.
that. I have to try. Why does it feel? I feel like it starts all the way up here.
It starts at 1. It's the exact same thing, moved 90 degrees to the left.
I did it wrong. Oh well.
That's all right. This number right here, this 90, is often signified by the letter Greek letter phi or phi. I'm not sure how. That's the phase. So this is going to become important in our talk later. A cosine and a sine are 90 degrees out of phase with each other.
This one's sine. This one's.
Yep. Sine starts at 0, cosine starts at 1. Now, some definitions of waves. This to here,
Wavelength.
also called lambda. Greek letter lambda.
Weird letter.
That's the Greek equivalent of an L.
You're rubbing off on me and it's getting me in trouble.
What's that?
I started writing in all capitals today and my academic writing teacher yelled at me. He was like, you can't do that.
Sorry. It's
It's easier to tell the letters apart.
It is. So,
Like all the P's and B's and Q's look the same lowercase.
when we talk about sound, it has a velocity through space, right?
How fast it moves. Well, that's not what-
1,100, like 1,100 feet per second.
Really? Does it travel faster underwater? Is that true?
Almost 8 times faster, I think.
Holy shiitakes. How come we can't hear it as well though? It sounds muffled.
It sounds high pitched. It's beyond our range of hearing.
So if you talk higher pitched underwater, would people be able to understand what you're saying?
They have to talk really low pitched. So here's where I'm going to get at. There is a propagation velocity through a medium. Velocity, V. Can I erase all this down here?
Yeah.
I'll erase this anyway. So V is how fast this wave's moving. If I drop a pebble in the water, you'd notice that the wave moves away from me.
Well, it moves away from the pebble, not you.
Correct. Well, if I drop it right at my feet, it's going to move away. But anyway.
If your feet are in the water, you've got bigger ripples than the pebble.
Not if I've stood there long enough.
All right.
Okay, so I don't need these. Oh, the other coordinate system's called a polar coordinate system. One of the things you'll be learning in your trig class with your fancy graphing calculator is how to do polar graphing. You get some really neat stuff out of that. Really pretty pictures, like flowers and stuff.
Daddy,
Honey,
why does it say we're getting something
I don't know, honey.
and just move?
So I know that this is a distance. Yeah?
Mm-hmm.
And your velocity is equal to distance over time, right?
Mm-hmm.
Feet per second, miles per hour, some distance over some unit time. So that means then that there's a relationship between point to point, the wavelength.
Isn't it cool?
What is it?
It's a Valentine.
My Valentine.
I don't understand what's cool about it other
It's
than
tie-dye.
It was all
Oh, okay.
black.
Oh, you scratched it off?
Yeah. And look, it's my name and Alicia's name.
That's neat.
Watch out, watch out. Get your hand off there.
Just move if you look at it long enough.
No, come on.
It's a sky.
No, I'm not helping you with anything right now.
Please.
No. I'm doing this. If you want to play on the computer, you may play on the computer, but you're going to do it without my help right now. So, the sound,
Wants it out. There's two.
velocity
Walking.
I sure went to some
in
different page.
air
Let it out.
at 1 STP, one standard temperature and pressure.
I'm just gonna move this over to this page. Okay,
Whatever.
can you give me a minute real quick? She told you no! Leave her alone!
Oh my gosh! Why won't anybody help me? I'm trying to.
Come here.
What?
Come here. Sit down. Using the computer is a privilege. You don't have to use it. If you cannot figure it out, I don't know how you could not figure it out. Then
My
you
friend
don't
made one
need
of
to
these.
play it.
My internet
Nobody
friend.
is required, needs, or wants to help you right now. Honey, I love you very much, but I'm in the middle of
Daddy,
doing
look at
this and
this.
teaching some stuff to your sister. And I'm going to be doing this for a while.
Thanks.
If you can't do what you think you want to do right now on the computer, do something different on the computer, or go read, or do something different completely. Okay? Okay? All right. I love you, hon.
See, it's a heart.
Uh-huh.
It's a box.
Cool.
It's Stuart's.
All right.
See? I got a piece of bubble gum too. It's a square!
Come on, honey. So I know that sound velocity in air at one standard pressure, temperature and pressure,
Do I draw that line?
no, don't worry about it, is about 1,100 feet per second. That's also, if you care, about 735 miles per hour.
That's fast.
Mm-hmm. So, if my wavelength, if lambda equals 1 foot, so if the top of the peak to the top of the peak is 1 foot,
What's the STP?
standard temperature and pressure, 25 degrees Celsius at 14.7 pounds per square inch. It's sea level pressure on a 25 degree centigrade day. That's like 75 degrees Fahrenheit, 72 degrees Fahrenheit.
That's comfy.
That's just like the normal day. That's what we call our standard day for these kind of measurements, because as it gets colder, the air squeezes, right? It contracts
Yes.
and gets thicker. And as it gets warmer, it gets spread out. less dense. So you have to choose a temperature for it to make sense, and you have to choose a pressure for it to make sense. So if lambda is 1 foot, how long, if I'm some guy, if you're standing right here, and this is some guy in a truck,
Oh.
honking his horn at you, and these are the sound waves coming by. If he's 1 foot away from you and he honks the horn, how long does it take before you hear that sound?
Less than a second.
Much less than a second, but how long? Speed, velocity, in feet per second times distance, or I'm sorry, seconds per feet. 1 over velocity. 1 over velocity. Feet, dang it. Feet per second is equal to seconds per foot is equal, and right now it's 1. So if I multiply that times feet, then I get time, right? Time. I shouldn't say seconds, I should say T for time. Feet per unit time. Inverted is time per unit feet times feet gives me time, right? Simple algebra. Okay. If I have a velocity, let's do it the other way. I have a velocity in feet per unit time. So distance per unit time, right?
Mm-hmm.
And if I divide that by some distance, some second distance, that will give me, I hate it when I do it all. If I take some distance and I divide it by the velocity, that gives me the time. D time D divided by D over T is equal to dt over D is equal to T. That's the math. Right? D over dt is equal to dd over t. The d's cancel out. I'm left with t. So, if my distance becomes my lambda,
1 foot.
and my velocity becomes this, we'll use the feet per second so their units are the same. That tells me that if I take 1 foot and I divide it by 1,100 feet per second, I'm going to end up with 1 over 1,100 seconds. 1/1100th of a second. 1,000th is a millisecond, so I'm going to round it and say that that's approximately 1 millisecond. It's more like 0.9. So that means it takes about 1/1000th of a second from the time that horn starts to make that noise to the time you get it in the ear. What that also means is in 1 second of you standing there, this wavelength happens how many times?
1,100.
1,100
Oh my
times.
gosh.
So when that guy lays on his horn at you, and 1,100 is actually that's about the pitch of my voice. That's about 1 kilohertz.
Oh, my hips hurt, Daddy.
I have a kind of a high-pitched voice. It's around 800 hertz or so. What, dear? No, it will be a long time. This is going a long, long way.
Oh yikes! How long?
Maybe another hour.
What time is it? It's 7. All right, it's cool.
No big deal. We'll go watch a movie after this.
Oh,
A good movie.
Show.
She already died.
No, she hasn't died yet.
All right. So what we got is a propagation velocity, and
Wait, I have to write that down still.
so what this means is 1100 feet per second means there's 1100 cycles. This is a cycle, one full time through. If I started here and went like this, that's one time. 2 cycles, 3 cycles, so on. It's 1100 cycles per second. And that's CPS. And nobody uses that term anymore.
CPS. That's Child Protective Services.
Oh my God.
What?
If they come to your house that often, it's probably too much.
They don't ever come to our house.
So, I'm just saying, if they ever come to your house that many times, it's too much.
Oh, I thought you were saying enough that you know what the acronym means, and I was like, that's what?
No.
1100 times. Oh my God.
Now,
Can you imagine 1100 times?
I know people that probably should have happened to at some point or another.
Oh my gosh.
Now, then the metric system,
Ugh.
this is named after, I don't remember his first name, Hertz. And it's H
ERTS.
ERTZ.
V.
Z. That's 1100
I've been waiting.
hertz. HZ. Capital H, little z.
No! It doesn't say not responding. Well, obviously it's not responding. How do you know? I can tell now.
So now, light travels at the speed of light. 300 million
Oh my gosh.
meters per second. Light travels so fast that civilization didn't even realize it was traveling for like 30,000 years, 20,000, well, over 10,000 years, meters per second. 300 million meters per second. The wavelength. So the wavelength of light can be pretty long, but the frequency is still pretty high, right? Because it goes by so fast. This is why sound velocity in water is closer to 8,000. Water is about 8,000 feet per second. FPS, feet per second. K means 1,000. Kilo. So that means that my voice underwater would be almost 8 kilohertz.
That's high pitched.
It's high pitched.
That's really high pitched.
It's fairly high pitched. And it would sound 8 kilohertz to you, even though I'm talking like this. As it hits the water, there's going to be a lot of energy lost at the interface between the air and the water, because it's a difference it's a change in medium. But once it goes through, if you're underwater and your ear's wet, it's going all the way down, you're going to hear it as though it's 8 kilohertz instead of 1 kilohertz.
So you probably wouldn't hear it.
You'd hear it, but it'd be high pitched, and a lot of the energy would be lost. So
if
that's
you
why
wanted
it
to
sounds
talk
dim.
to somebody, you'd have to talk low.
I don't think you could talk that low. Actually, like, no, you couldn't talk that low, but they actually, for like people who are doing saturation dives where they're breathing helium, so they sound like Donald Duck and you can't
That's
understand
bad for
them.
you. It's bad for your brain.
Nah, it's not that bad. It's fine. But what they do is they actually use descramblers when they talk to them from the surface, so that when they talk, it shifts their frequencies back down to where you can hear them and understand them. Because they are really hard to understand. I mean, they're breathing helium for like 30 days at a time. Dude, that's scuba diving. We're not going to go into scuba diving today.
30 days?
Yeah.
What?
Saturation diving, they'll go in a bell and they'll stay in a decompression chamber for 30 days straight.
Until they can come back out onto land?
They spend about 2 or 3 days being pressed down to whatever depth, up to about 1,000 feet. And then the decompression time is about a week. So if it's going to take you a week and a day just to go do one job, why not put you in a bell, press you down, and move you from job to job to job to job where they need somebody pressed and save the time, so you just stay pressed. That's what they do. And so OSHA rules and everything else, they run about 30 days. I think 45 days is the absolute maximum before stuff. But
Light.
so, now, light is an electromagnetic wave. Electricity running through a wire is an electromagnetic wave. Radio is an electromagnetic wave.
Microwaves?
Microwaves are electromagnetic waves. Electromagnetic waves start from a source, just like throwing a drop in the water, right? If I throw a rock in the water, they propagate out from a source like this, right? Right? And they propagate forever outward until something absorbs them or whatever, right? It runs into a shore or reflects them or whatever. And of course, obviously the same amount of energy is getting spread over more and more areas, so they get weaker. Their attenuation goes down or up. So if I look at a ray of light, so I'm going to call this X, this Y, and this Z. And I'm going to do this. And I'm going to do this. So these lines here that I'm drawing in right now are trying to signify that this sine wave is in the plane of the x-axis here. So it's perfectly in plane. It doesn't lean out any, it doesn't twist, it's straight down the z-axis. And then at the same
that?
time,
My lines are ugly.
it's all right.
Looks like DNA. I feel like I already said that.
You did already say that before you decided we should start over and actually record. These lines.
Look how ugly mine are.
It doesn't matter. These lines are trying to indicate that these are in the plane of the y-axis. So these ones are going this way, and these ones are going this way. No, Adam.
Wait, it usually takes this long.
Like this,
Oh, Daddy.
right?
Mhm.
So these ones are up. These
I think
ones
he
are.
has a serious question.
What is it, Adam?
Are you almost done?
No, honey, long time.
Oh.
Hours, Adam, hours.
Uh,
I'm teaching freshman level physics.
Daddy.
Adam, honey, what did I say?
go on, help him. It's okay. It's gonna take you like 5 minutes. Go ahead.
All right, well, let's pause this for, well, I'll cut it out later. What? Yeah, no, what?
So, I just supposed to start with this game. But then I don't want to subscribe.
You can't,
Why?
because you don't have an account.
Well, this is Kelly, and she said that I can play.
You'll have to ask.
Leah, can you help me get the sky wolves? Daddy,
What?
can I take a bath in the bathtub?
No. There you go, skywars.com. That's it. Apparently. All right.
Do that. Less than 5 minutes.
Yeah, I might not even have to cut it out.
Oh, Daddy.
1.
Sorry, but I don't know why. But whenever I log in, when I'm using your account or my account, it's always blurry. Like,
That's something with the computer. That doesn't have anything to do with the account.
Callie, do you have any chocolate?
This is the,
Put your eraser on my paper.
I don't know which one's which. I don't remember. I think this is the E field, which is the electric field. And this is the H field, which is the magnetic field.
Why isn't it M?
H. H and B. E, H, B, and another one. Depends on the notation you're using.
But if it's
So-
magnetic, why isn't it M? Is M something else?
Yeah.
Okay.
I don't know what off the top of my head, but H, B, there's a B field, there's an H field, and there's an E field. And they're related. So an electromagnetic wave, when we're talking about an electromagnetic wave, it has an E field and an H field. And what happens is this one collapses and causes that one to grow. So energy stored in this field, as this collapses, gets put into this field. And then as this collapses, it gets pushed back into that field.
So it's like continuous collapsing.
It is in a vacuum, it will go on forever.
But
It'll
we're not
get-
in a vacuum.
It'll get weaker and weaker and weaker as it spreads out, but the waves will go forever.
So even if you can't see it, there's still light there.
To the point that it's not detectable, it will still be there. All the suns, all the stars, all the heat given off in the universe is bouncing around all over the place. As long as you're within the speed of light of it. You know, when we talk about seeing a supernova in the sky, that supernova happened 15,000 years ago maybe. And it's just now getting here. It's 15,000 light years away.
So when we see comets, are they actually like when you see it, is it actually in a different spot?
Very slightly different spot. When you see this pen, even though you see it moving, there's time that it takes for the light to get to your eye and to process. So we are living in the past. We are constantly living about 30 milliseconds in the past. There's a very neat experiment you can do to screw with people. That's along those lines. It uses a button and a light and a delay.
Let's do it.
Yeah, not right now. We'll do it some other day.
I got a light.
And it requires some electronics. All right.
Oh,
So-
I'll roll back over.
We're getting up to where we were going to get to originally. What is
that?
special about a laser light?
Oh yeah!
So we're talking about sines, we're talking about wavelength, we're talking about sine waves, we're talking about an E field, H field. What's special about laser light?
They're concentrated? I don't know.
It is
It's colored.
light, amplification.
What? It stands for something?
Through stimulated
Oh my gosh, I gotta write this down.
emission of radiation. You want me to explain how a laser works? Or do you want to save that for another day?
How long is it gonna take?
Yeah, I can do the quick version in about 10 minutes.
Alright, let me write this down first. We'll go back and do it another day. I gotta find out if she dies. I gotta find out what's in the closet. She went down this hallway to like all these doors were locked except this one, and she went in and closed herself in it, and she went to go reach for a light switch, and then I had to go eat dinner.
And she grabbed a perv's penis instead.
Probably a dead person's.
It's a ghost. She reached to flip the switch and like did this to a
Oh.
ghost's nose.
Ow!
That's right. And now it's poltergeist.
No, there's
Gonna
no.
suck the whole house in.
I don't think there's ghosts in this season. There was ghosts in last season. Last season was called Murder House. Everybody died. This one girl killed herself and didn't know it.
You have a medium. The medium is a semiconductor, generally speaking.
Page.
The electrons if I've got an atom with electrons zipping around it and whatever, this is not correct, but so like hydrogen has 2 atoms, right? Or 2 electrons, right? And it has, no, that's helium. Hydrogen has a single and it has a proton, so it has a P and an E out here,
Oh my gosh, you made me erase it.
right? This is hydrogen. Put a little minus by the end.
Negative.
If I bring energy into this system, the system reacts depending on the type of radiation. It can cause it all to vibrate. That's what heat is the thermal motion of atoms. But you can cause, if it's high enough frequency, certain colors of light, for instance, or
Right.
gamma rays or X-rays or whatever, can cause this electron to jump up to the next valence band.
That's weird. Then it's not the same thing.
No, it is. It's still just one, but it's in a higher energy state. What happens is, at some point, when I quit letting energy in, this thing falls back into the original energy state, and it has to let that energy back out. So I've added energy to the system, the electron has moved out, and it turns out they're discrete levels. It's discrete positions that it can move to. And this is quantum physics, and I don't understand, when you get down into the quantum physics of it, I don't understand that word. Not well enough to explain it anyway.
Maybe one day I'll be able to teach you.
That'd be great. So when I quit adding energy to the system, then he can fall back in. And when he does that, he gives that energy back off, right?
Ah, yes.
Newton's laws, right? Energy can neither be created nor destroyed, but it can change form. So energy came in, it got absorbed, it changed form by moving this electron out here. Now when this electron falls back in, it lets that energy back out. When that electron falls in, that energy is released as light. The frequency of that light is based on basically how far of an energy state it dropped.
It goes into this medium thing, this line.
So now I have some medium.
No, you erased the box.
I'm just moving it down.
Mine went through the box.
So now what I do is, in a ruby laser, it actually has a flash tube around it.
What's a flash tube?
It's like a flash bulb. It's a tube that wraps around it. And this is actually ruby,
Like the...
the gem. It's a big chunk of ruby.
Is that expensive?
Yeah, but you can make them, you can have them made and grown. It's all one single crystal. And they put a coating on the end.
Is that just your line? Is what that
Yeah,
is?
it's a coating. On one end, the coating is really, it's like a mirror, actually. And this end is like those, if you go to a store and they have those see-through mirrors, where they're like watching you from the other side,
You know how to tell?
you can see through it if there's lights on. I know.
Like in Beth's, in the...
And you can put the thing on it and see where the reflection is. If the reflection's directly underneath your thumb, then it's a fake mirror.
What if you're in a bathroom and it's like that?
It won't be. That'd be illegal.
That's so creepy!
So I'll make this one dimmer.
But in Beth's office, like you go, not her office, but you go through in the lobby, and it's like, it looks like a mirror, but if you look close enough, you can see through into like the secretariat room, and I'm just like, makes my head hurt.
Okay, so what happens in a ruby laser, and this is generally the same for all lasers, but they use different energy sources. The flash goes off, poof. A bunch of this light goes into the medium.
It has to be squiggly lines.
That's how you show that it's energy usually. It's energy going in as opposed to a straight line. Inside, what happens is all these little atoms laying around with their electrons floating around, they all jump valence bands like they did here. All this light, wham, comes in here. All these electrons pop out to the next energy band. And then what happens? That light goes away. And so now all these electrons fall back in and they give off light. Here's what's interesting.
Is it red because the ruby's red?
No, it's red because of, it's whatever color it is because of this band gap.
Well, then why does it matter if you use a ruby opposed to like an emerald or a sapphire or a diamond?
It has to do with the semiconductor characteristics of it.
Okay.
Some things that work.
Science.
It gets into semiconductor physics. I have a whole book on that downstairs if you want to read it someday when you're really bored. It has symbols that I haven't used since college in it. Like del and grad and some other weird things. And
Some other weird things.
it has three-dimensional integrals.
What is that?
Calc 3 plus differential equations.
I'm not even in pre-calc.
Right. So we don't want to go there.
I'm not even
So
in algebra
so we're
2.
going to take a step back now and talk about the light inside this tube. I'm gonna draw this a couple different times. So
How many different times?
I don't know. So I have an electron that falls back in, and some light goes this way, right? And I have another one here. He falls back in. I get some light that goes this way. But some percentage of this, I get light doing this, right? Going this way and that way. So some of it escapes out the sides, but some of it goes along the length of the rod, right? So now this rod's pretty short, and this stuff's all moving at the speed of light, so they're moving pretty quick. So I get a wave that goes boing, boing, bounces back and forth. So and then I have another light beam, another photon of light that's traveling along, and it's doing this. And I have another one that's doing this.
And they all keep bouncing back on themselves?
Ideally, this is a machined length, so it's an exact length, but it's not usually quite that awesome. If I have two waves, so this is all energy and it's all in the same place, so I'll draw it all on the same axis, right? If I have a sine wave doing this, and I have another one that's 90 degrees out of phase, I'm sorry, 180 degrees out of phase. So, there to here. (180 degrees out of phase). If I add those two sine waves together, if I say sine of theta plus the sine of theta plus 180,
Like 3 people just go
what's that equal?
to their room. It's hard.
This is a very interesting concept, and it's true for sound waves.
Yes.
It's true for light waves. It's true for any kind of wave. And this blows people's minds. It doesn't make intuitive sense. It even happens in water.
No. What is it?
0.
What? That doesn't work.
It
That's
does.
not right.
It's absolutely right. This energy is being added while this energy is being taken away. This
Oh.
energy is being added while this energy is being taken away.
So it balances it out.
It balances out to 0.
Oh my gosh.
Total of no energy. That's how those fancy noise canceling headphones, that's how they work. They actually have a little speaker right there next to your ear, and it listens to the sound coming in, and it recreates it right out of phase so that it nulls it. It's called destructive.
So it equals 0.
Equals 0.
That's so weird. Oh my god. Oh! Did you hear that?
Yep. It's called, listen to me,
I'm listening.
destructive interference. So you can imagine then that there's probably something called constructive, which is the opposite of destructive, right? Interference. If I take the sine of theta plus the sine of theta,
E's in the word interference.
yeah, if I take sine of theta plus sine of theta, then my output is 2 sine of theta, right?
Yes.
Which is what you were talking about before. If they're perfectly in phase. If they're out of phase like this, what happens? I get da 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 da, but now I get this plus this, right? So now I get this going up, but now this is going down at the same rate that's going up, so it kind of flattens off. But now they're both going down, and I get a funky waveform that's something in between. It's some addition of them, and I can't do that without a graphing calculator or a computer program. So imagine inside of our rod here, there's some that are going this way and some that are going that way, and I've got all these waves doing this. A fair number of them are going to cancel out, right?
So it would be really concentrated, right?
So all of the ones that are exactly 180 degrees out of phase go away. Ones that are a little bit out, so that one's right out, right? But some of the ones that aren't 180 degrees out, they start creating new waves, 2 different waves, and all these other waves, they constructively interfere, and they create a big wave. Many big waves. And it's actually, so it's not big waves, they're all the same size wave, they're just a gob of them, right? They're all, so the first laser light, rule number 1, if they're all exactly in phase, well, that's number 1. All waves are in phase. That means they're all in the exact same phase. And that has repercussions down the road. That means something. Rule number 2, if they're all exactly the same phase, that means they're all exactly the same wavelength, right? Which means 2, monochromatic.
They're all the same color.
All the same color.
Because color is wavelength,
Mono
based on wavelength, right?
equals 1,
Chromatic
color.
is color. I learned that in art. Because color is based on wavelength.
Laser light, all waves being in phase, that's called coherent.
almost done.
Getting there. I want to say that the scientists who did it were Michelson and Morley. If I take a laser, I'll just draw a laser pointer for
Is there only 2 rules?
all the same color, all in phase.
That's it.
It's a falling from those 2 rules means it doesn't spread much. So if I took a laser pointer right here on the Earth and it had perfect optics and everything, and I pointed it at the moon, when it would get to the moon, it would still only be a dot this big. I mean,
So you wouldn't see it.
the truth is it will spread out some, but
Not much.
not a lot. There's, I think they call it a coherency length when you talk about lasers, now they're starting to talk about the effects of the optics and everything else. But so if I take a laser,
Beautiful.
and I shoot it at a wall.
I'm drawing mine pointing down.
But this wall,
Is that okay?
yeah, has a slit in it. What do you think, and there's a projection screen on the back side of the wall. Clearly that's a narrow slit. Because if it was, if it was a doorway, the laser beam just goes right through. So this is a really narrow slit. What do you think gets projected on the back wall? So let's look at this slit like this, and my beam's this big. What do you think gets projected back here on the back wall?
That little rectangle. That's. What?
Can you let the cat in? He's out there meowing. I think that's him out there.
He's not outside.
I hear him meowing. Is he out there?
No, he's not. You can't hear him through the door.
Yeah, you can.
He's not out there. I don't know.
You don't. What you get on this wall as it passes through, if I kind of turn this way,
Oh, my knees.
and it's landing on the wall here, I get a Gaussian distribution. So that means I get over here, it's dim, brighter, 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 dimmer, 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 dimmer. So this is intensity, how bright it is, and this is space, distance. On this wall, what I see is it's completely dark over here, and it gets brighter and brighter and brighter as I come in, and it follows a Gaussian distribution. If I put 2 slits in there, magic happens. If I put 2 slits in there, magic happens. This drove a lot of people up the wall for a long, long time. I can't tell you the math behind it. What you get now is 2 distinct bands with smaller, dimmer bands in between.
Like a barcode.
That's one way to look at it. What it is the interaction of this light. If you imagine that this slit is like this, right? And the light is coming in this way. Some of the light bounces off the edge here and goes this way. Some bounces and goes this way. Some goes straight through. And there's all sorts of differences in between, right? So that means here the phase front,
It goes out.
now it starts to do this, right?
So the one that goes straight through will always be the brightest because it doesn't
okay.
go as far.
Well, no, because most of them are going straight through, but some come off to the side. Fewer come off to the sides. But now we start talking about our phase lengths before and how they're in phase. Okay, so these are all still in phase with the first, but So when this one strikes here, let's say it's at 0 degrees, but when this one's, so this is 0 degrees along this line, right? Does that make sense? Because it's the distance, time and distance and speed. So when this one hits, it's maybe 2 degrees. And when that one hits, it's maybe 4 degrees. And when this one hits, you know, minus 2 degrees, minus 4 degrees, and so on. Now, when I've got the second hole over here, and this is going on again, another beam coming in, and it's splattering all over the place, and its 0 degree phase front looks like this. He's got a bright spot there, and he's got a bright spot there. But now these all destructively interfere until you find some spot here in the middle where they're about the same length, and now you get a bright spot again. And then they destructively interfere, and then you get a bright spot, and then you get the big bright spot, and then because you got some of these that are coming way over here like this, and some, and so you actually get a pattern of lines.
A barcode.
It's not a barcode, but
It looks like a barcode.
But if I change the distance apart that these are, these change. Now, this is a Michelson interferometer.
Okay, Daddy.
What?
Are we almost done?
We are almost done. I realize you're getting tired. We are almost done.
Ow.
I take one laser.
Wait. What a cat? Oh. Somebody just made a noise. It's probably you.
I'm going to take one laser. I have a mirror that's a 50% mirror. That means half the light goes this way and half the light goes this way. Okay?
Can I have some paper from your office?
Yes. Just 2 pieces, no more. Careful, hon. Thank you.
TV.
What?
I watch TV.
Not if you're getting paper out of my office.
I'm not getting paper anymore.
She needed more than 2 sheets.
Yeah, go ahead.
Thank you.
Light bounces, runs this way, hits a mirror, comes back down. Now this is all in phase. It's one beam coming down. Bing, 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 bing. And these are all really close together. I'm drawing this really. So effectively I've got light going this way and I've got light going this way. And now I have a double slit. So I have one beam of light comes in and I have a second beam of light comes in and hits. I don't even need a slit actually. These 2 things are going to make an interference pattern, aren't they? This one's going to have blurs this way. This one's going to have blurs this way. And you're going to find speckles and bright spots, and it's going to have a pattern. It's going to have some pattern here, whatever that pattern is, right? Because light went this way and light went that way, and by the time they got here, they were out of phase. We don't know what the phase was, but we know that they're out of phase because of this interference pattern. And as long as that interference pattern doesn't change, we know what? Nothing's moved. So if this is like 5 miles, and this is like 5 miles, and there's an earthquake, let's say there's an earthquake, and this distance changes to 5.000000001 miles, the interference pattern changes, right? Because, I mean, we're talking wavelengths of light here. They're literally nanometers, billionths of a meter. Almost trillionths of a meter, half a trillionth of a meter for green light or yellow light. So if there's an earthquake, this interference pattern goes whoa, and then goes back to something new. And we have to recalibrate our instrument to say, oh, this is the new pattern. LIGO, a gravity wave comes rolling through. A gravity wave is an actual stretching of space-time.
How does that happen?
Relativity, beyond my ken. This is what I was talking about, the difference between Einstein's rules and Carver-Mead's rules, and which one's correct. This experiment detects them differently. If it's Einstein's rules, it's a change of this distance. If it's Carver-Mead's rules, it's a change in the something to do with the mirror. I want to say it's the it's a vector property of the mirror moving, and it's different, and you would detect them in different ways. And the LIGO, I think it's LIGO, light large interferometry or interferometric gravity wave thing. Observatory is detecting small changes in either this distance or this distance. They usually have two of them set up so you can say it happened here and then it happened here, so that you know which direction it all happened in. And it can also detect the change that happens at the mirror. And so just this week, they confirmed, with the help of scientists in France who have a similar big array over there, they agreed between the two of them that a gravity wave was detected. What we haven't heard yet is, does it do Carver-Mead's? Does it confirm Carver-Mead? Or does it confirm Einstein? And that's what the last hour and a half has been about. This is how they detected a gravity wave, and it goes back to fundamental physics and lasers and light and trig, and why math is important if you want to do neat things. This is actually pretty freaking cool.
It is.
Because this thing will detect changes in length that are on the order of a width of a proton. That's teeny tiny. And that is the end of our story for today. And probably for the next 2 months, right?
I don't know. When I'm awake, we can do it again.
Next, we can talk about nuclear fission and nuclear fusion.
That sounds fun. Let's do that. Not right now.
And how an atom bomb works.
I already know how that works.
And how styrofoam is an important ingredient.
Really?
Yeah.